Hello. All right. Okay. Welcome to the Python That Wasn't with Larry Hastings. He's a Python core contributor. He's going to use the full 30 minutes to present, and he's got a lot of slides, but you're welcome to talk to him after the talk if you want to discuss further. Thanks.
All right, ladies and gentlemen, boys and girls, children of all ages, this is the Python That Wasn't, a half-hour survey of ways in which the Python language did not change. Let's talk about changing the Python language. It's very easy to propose changes to the language. In fact, it seems like every week some newbie shows up in Python dev and says, you know what would make Python better? You make arrays start at 1, and you make range go from 1 to n. And it's all you can do to keep from strangling these people. It's very easy to propose changes. It's very hard to get changes actually into the language. Not only is it you have to implement it, but there is a whole bunch of stuff that you have to go through in order to change the language. And this is intentional. Python has a large, fiercely protective community around it, and any proposed change is held up to intensive scrutiny. So I like to say only the finest tuna gets to be Python. Consider what happens when you make your language too easy to change. You might wind up with something like PHP, which, after 14 years of existence on this planet, decided it could no longer live without the goto statement and added it in 2009 with version 5.3. Now, I like to think of the progression of a proposed language change as a sort of a hero's journey. You must start by posting to Python ideas. And there you meet the hordes of Usenet. If you survive these initial sorties and you level up, you must proceed to Python dev, where the monsters only get stronger. You must continually navigate the dismal swamps of backwards compatibility, the icy caves of Pythonicness, the stark windswept plains of genuine necessity. And if you endure all these and you reach the valley of the pep, you face the greatest monster of them all. So brutal, so unyielding, it has been known to eat its own children. The BFDL. And if the BFDL gives you his blessing, then you can proceed beyond to the glimmering treasures of actually checking your code into Python. But none of these did. So let's talk about the first one, the freeze protocol proposed by Barry Warsaw back in 2005. The problem, as Barry saw it, hashable objects are useful. You can use them as keys in a dict. You can use them as elements in a set. But gosh darn it, mutable objects like lists and dicts aren't hashable. We'd like them to be hashable, so we want a way of commuting mutable to immutable. So the proposal was a new top-level function called freeze. Freeze would convert a mutable object into an immutable equivalent. So if you call it with an already immutable object, it would just return that object again. So if you call freeze with a list, you get a tuple. You call freeze with a set, you get a frozen set. You call it with a dict, and you get this hypothetical frozen dict that was not particularly specified, but we'll assume that it's going to exist. And if you call it with a tuple, of course, you get a tuple back. Underneath this, there would be a new underscore method called freeze, which would return the immutable form of self. So what happened to this? Raymond Hettinger, let me start with, there really wasn't much of a use case as far as anybody could see. I actually asked Barry recently, and he said he couldn't remember what he wanted it for. And in fact, Raymond Hettinger really didn't like this PEP. He posed himself as an anti-champion to it. Saying things like, it doesn't make sense for arbitrary user-defined objects. It barely makes sense for things like sets and lists. It would lead to hard-to-find bugs, particularly as the objects started to drift. You continue to mutate the original object. And he called it a Liskov violation, which, if you were in the previous session, you know that's a term he likes to throw around. By that, he means a violation of the Liskov substitution principle. So let's talk about matrix operations. There were actually two different PEPs proposed around the same time. This was pretty early in the PEP process. I believe what happened actually is the author of PEP 225, Hayazu, I can't pronounce it, they were talking about this on Python Dev a lot, and I think Greg Wilson's PEP was written first, was actually a response to the discussion that this gentleman was bringing forth. So the problem as they saw it is that matrix operations are terribly, terribly important in numerical programming. If you have an array or a matrix A and another one B, you want to multiply them together, and you're doing this just all the time. But matrix multiplication is element-wise. You're examining the elements inside of the matrices. You're not multiplying the objects themselves. And so you really want to be able to multiply them very easily. And they said function calls are just too much to type. We don't want that. We really want operators. And in fact, PEP 211 specifically says, quote unquote, numerical programmers really do care whether they have to write mmol A, comma B instead of A op B. So PEP 211 proposed one new operator, the across operator spelled @sign. And I'll point out that this is 2000 decorators with @signs. Those were Python 2004 with 2.4. So this predates decorator, so it wasn't going to collide back then. So the idea is that you can rewrite the one on the left as the one on the right. You can iterate over two things at the same time with only one for loop. This was not enough for PEP 225, which proposed a total of 6 new operators. These are the standard math operators, plus, minus, times, divide, mod, and power, all with a tilde added in front to distinguish them as element-wise operators. And to complement these, we also added 6 new augmented assignment operators, adding the equal sign on the end, for a total of 12 new operators. For what it's worth, I think that the tilde equals is the same as the @ sign, so clearly these weren't both going to go in. Now, what happened to this? Well, in general, there just aren't that many numerical programmers. There are a lot of Pythonistas, and very few of them are doing numerics. So the need for lots of new operators in the language to support people who aren't using it yet, it didn't fly. There were some arguments that adding these numerical arguments would bring new hordes of numeric programmers to Python, which was just viewed with a dubious eye. In particular, people said, you know, Python programmers do a lot of text processing, and yet there are no specialized operators for text processing. Now, are there? Why do you guys get hordes of new operators when we don't get anything? For what it's worth, people tended to like 211 more than 225 just because it was only one new operator as opposed to 12. Of course, you could always write it with ItterTools product. You could cache that locally if you wanted to make it easier to spell. And really, I always thought that the right approach was to use undermol and have your own user-defined objects, which would actually do the element-wise operations, which is what SciPy does. So let's talk about another. Well, this is interesting. This is make none callable, PEP 336. The problem, as posed by the author, consider the following. You have 3 callables, and we have a function that's acting as a sort of a dispatch to those callables. It takes a name argument, and then it looks that up in a dictionary. So what happens if you call this with a key that isn't in the dictionary? Well, it's going to return none, and then you're going to call it, and then you're going to throw an exception. That's terrible. So the obvious solution is that you make none callable. None would consume all of its arguments. It would return none, which would allow you to call and call and call forever and ever. And now that code on the previous slide would work. Reaction to this proposal was mixed, and by that I mean it was not mixed. Raymond Hettinger said, this made people's stomachs churn. Tim Peters said, even Roman numeral literals are more Pythonic. Guido von Rossum said, not while I'm alive. So let's talk about one that was a little more likely, the switch case statement. This was first proposed in 2001 with an initial PEP for Python 2, and then Guido von Rossum himself wrote a PEP for Python 3, PEP 3103, in 2006. Now remember what I said about the BFDL eating his own children. This is what I meant. We have a PEP written by Guido von Rossum and rejected by Guido von Rossum. This is not an isolated incident. PEP 254, making classes look like types. This was actually just a stub. It never was a fully fledged PEP. It was just like yeah, we want to make classes look like types. I'm going to fill this in later. Oops, it already happened in 2.2. I'm rejecting this. PEP 259, omit printing new line after new line. This was an idea where the print statement, the print statement If you passed in a series of stuff, if the last one was a string, and the string ended with a new line, hey, we could just not make print emit its own new line, and that might be nice. And the community reaction to this was, stop messing with print. This is too magical. And the remaining one is anonymous block statements. This was when, what happened was this PEP was rejected in favor of the with statement. This is actually a more powerful proposal. This is, the anonymous block statement was kind of like the with statement. It had an enter and it had an exit, but it also got passed in as a parameter the anonymous code block that was going to be passed in, or was passed in. So you could call it 1 time, or you could call it 0 times, or you could call it 3 times, or you could call it as many times as you want. And so this was embedding flow control inside of this statement, which was kind of a way of you creating your own new flow control. In the rejection of the PEP, Guido said that he read an essay by Raymond Chen that said hiding flow control inside of macros is a bad idea. And so he was like, yeah, it is a bad idea. Why was I proposing this? This is a bad idea. I'm rejecting it. And so we got the with statement, which I think everybody likes. So let's talk about the Seaswitch statement. This is a very quick overview for those of you who aren't familiar with C programming. Here we have some C code. We're examining a value called x, and we're looking at it several times. If x is this, else x is this, else x is this, else do something at the bottom. This is a pretty common programming idiom. And when they designed C, they said, you know what, let's make this a little bit easier. So they added the switch statement. You switch on the value that you're examining, and then you have cases for each of the individual possible values that you're interested in, and you have a default statement at the bottom that handles it if it's none of the above. I think this does a good job of sort of making it very pretty looking. It really isolates what's interesting and different about this particular section of code. But it also allows C to do some optimization that it wouldn't otherwise be able to do with just a series of if statements. A switch statement can be optimized a couple of different ways. I actually worked at a compiler company, and a developer there told me they had 3 different strategies. They could do a nested if tree, they could do a jump table, and they could do a perfect hash, and they would figure out at compile time which one of those would be best. And so it sure would be nice if Python had something like this, but it doesn't, and it never has, and it's something that people wanted for a long time. So let's talk about what it would look like in Python. If you wanted to write this in Python today, you just have to write a series of if statements. Or you could write a dict like this. This has been brought up a lot of times when people say they want a case statement or switch statement. You make the values that you want to have as case statements keys in a dict, and then the values are callables, and then if you want to have a default, then you use get instead of just square brackets, and you pass in the default as the end, and then you just call it whatever it is. And the problem with this is it's still not all that fast if you have it inside of your function because you have to build the dict at runtime every time. And if you build the dict at module scope, so you only build it once, now you've sort of broken your code into little pieces and it's not as legible anymore. So it would be nice to have a real switch statement in Python. So I'm going to talk more about the 3000 version than 275. 275 just said, let's have a switch statement, here's what it should look like. Guido really went very deep into the possible implementation. So this is the proposed syntax for both 275 and 3103. 3103 went over a bunch of alternative syntaxes that had to do with, like, do we indent case or not? Do we even need the case statement? Guido said, no, this is the right one. And this is the one proposed by 275. So we have the case, we have the syntax all hammered down, but what do we do about the runtime semantics of this? If we generate this as a series of else-if statements, then we really haven't done any better than what you can already do, which means this is just an alternate spelling of something we can already do. That's not interesting. So let's not bother. Let's not even consider doing that. If this is worth doing at all, we're not doing if-else-if statements. So we're going to have what Guido called the dict dispatch, which is very much like the code that we were writing before by hand, but we would do it under the covers and we have this nice syntax on top of it. The problem is that with a dict, you have to know the values of the dict in advance unless you're building it every time. And if you're building it every time, again, this is no better than what you can already do in Python, let's not bother. But this is a problem because Python is an awfully dynamic language, and having static expressions is a kind of a kneecapping for what you can express. So let's talk about case statements and static expressions. Here's a case statement with a switch statement with only static expressions. That would be pretty miserable to maintain, particularly if any of these were meant to be symbolic, like, you know, if this was a token or something like that. I'll show you that in a minute. So these are all static. These will all be known at compile time, and you wouldn't be interested in using this statement very much. On the other hand, here's an awfully dynamic switch statement. You have callables, you have an object that's created at runtime. There's no way that they could cache this information in advance. You'd have to build the dict every time, and again, we've lost. But there is kind of a happy medium. What if we have sort of mildly dynamic expressions? These are variable lookups, but we're not really expecting them to change. So this is a bad example of a tokenizer. We have a parser, we're switching on a token stream. I should say, by the way, that the case statements are pretty frequently used inside of iteration. You have a series of things you're iterating over and you're examining each one in turn. So like message loops for windowing systems or tokenizers. All you very commonly use case statements, switch statements. So we would like to write code like this, but the problem is that parser.identifier is a runtime dynamic expression, and we can't really cache that in advance without breaking something in Python. But maybe we could get away with breaking it anyway. So let's talk about the lifetime of a young function. There are really three different moments that are important in the lifetime of a function. There's tokenization, or compile time. This is when the tokenizer is iterating over your script, and it's generating a token stream as a result of what it sees. And when it sees def foo : it emits a token called make function. And then later on, when you call the function, it's going to emit a token called call function. Then, once it's done tokenizing the file, it starts at the top of the tokenized file, and now it's going to be iterating and calling all of those tokens. And when we hit make function, that's when we take this, we have at that point we have a blob of the bytecodes that we want to bind the function name to, and we have the function name, and we store it at runtime in a symbol table. And so this is what's referred to as definition time of the function. And then we get to an actual call to foo, a make function, a call function token, and that's when we call the function. That's runtime. So tokenization time, that's terrible. If we do that, then we're restricted to static expressions, and case statements are not interesting. Switch statements, I should say. If we do it at runtime, then we're building it every time, and that's terrible, because now we're eating the cost of building the dict every time. But make function is actually kind of a happy medium here. And what's interesting is we already have an example of something, of values that are bound at make function time, which is default parameters. You can say anything you like as a default parameter. It can be a dynamic expression. And what happens is when you get to the make function call, they evaluate that expression, they store it away in a list. And so it doesn't actually change over the lifetime. You can call the function 1,000,000 times, and that value is never going to change. You could do the same thing with values for a case statement, and that seems like it would work pretty well. And in fact, the whole thing seemed like it would work pretty well for all things respected. So what happened? Well, what happened was, at PyCon 2007, Guido still wasn't sure what to do about this. And so he apparently took a show of hands at the keynote, and people just were not emphatically for it enough. And so he said, all right, I'm killing it. So if any of you were at PyCon 2007 and you didn't vote the right way, then because I really wanted this. So let's go back to a very early PEP. This was so early, they were still kind of figuring out what PEPs meant and what you needed and what you didn't. This is Range Literals by Thomas Wouters, or Wooters, I'm not sure what to say. So again, this was sort of a hazy, crazy, like slapdash, PEPs. Let's write a PEP for this, let's try it out. So the idea here is, range is wordy. Range can be overridden. You could set range to something and now you've broken people's code. Range, you can't optimize it because it's a runtime call. You might be able to generate specialized bytecode that would be faster if you knew what a range was at compile time. Range is inconsistent with slice syntax. Range is a function call. Slices have square brackets and colons and things. It sure would be nice if ranges and slices looked the same, wouldn't it? So let's do that. The idea is that you would have square brackets without an iterable in front, and you'd have some colons inside, and that would return a list. This was also, like, again, 2000, we were just getting iterators, and it was like, should we have this be an iterator? Nah, Guido said, make it a list, it's better. So this would return a list. So now you could write your for statement over 0 to 9 as for I in square brackets colon 10, which is a little shorter, it's kind of nice. At the time that the PEP was written, people were like, should I write a PEP for this? And people said, don't bother, just write the patch and check it in, everybody wants this. Over the intervening time between when he wrote the PEP and sort of like thinking about it, Guido said, you know what, I don't actually think I want this. And he never really went into why it was. When Thomas Wouters checked in the rejected PEP, he wrote in the comment, it was like, I don't know why he said, but he said, and so maybe we can figure this out later and document it. But I mean, don't worry about it. I actually asked Thomas about this, and he said, you know what, I think it's better that it didn't go into the language. I'm happy about it. I was happy about it then. I think this is fine. The one thing that was mentioned in the rejection notice was that there were a couple of dark corners. I think they were sort of looking for problems, to be honest. There was a proposal that instead of only taking integers, you could also have floats, and you could have float range literals, and maybe you could have strings, and you could, individual characters, and you could increment those, and you could have iteration which produce, a list of A, comma B, comma C, comma D, comma E. I don't think that would have happened if they had actually gone through with this. The other thing was people proposed this wacky thing where you could actually embed range literals in the middle of other things inside of a list. And again, this is just too weird. But again, I think if people were really serious about this, that they just wouldn't have bothered doing this. They would have just cut that out and done real range literals. So the last one we'll talk about is dynamic attribute access. This was proposed in 2007, and the conversation happened very quickly. It was over 2 days. It was in Python Dev, I think, one of those. It never it never made it to PEP status. It was just discussed, and people were initially very interested. Well, I'll talk about it. So the idea is getAdder, setAdder, delAdder. These are unattractive. These are clumsy. These are wordy. People don't use getAdder and setAdder and delAdder because nobody wants to spell it. And so if we had a new syntax for this that made it much nicer, much easier to get at the attributes with dynamic expressions, then people would do all sorts of new and wonderful and unique things. So the proposed syntax, it was hashed out. There were a bunch of different proposals, and this is the one that everybody settled on, was O dot square brackets. And then the expression inside would be used. This is equivalent to setAdder, delAdder, and getAdder, and depending on what context it's in. If it's just all by itself as a right-hand value, then it's going to be getAdder. If you use it in del, it's delAdder. If you use it as an assignment, it's setAdder. So you have everything covered. I should say, however, that this is 2-argument getAdder, not 3-argument. There is no way to specify default with this syntax, and if the attribute doesn't exist, you're going to throw an exception. So what happened here? Well, first, there really wasn't a problem exactly. There was, I just did some statistics. At the time I did the grepping for the version then. I just did it last week with the release of Python 3.2. And everything in star.py underneath lib, I counted all the lines, I counted all the calls to 2-argument adder, because that's the only version that's going to be, this is the most commonly used thing, and it doesn't handle 3-argument. And it was 0.08% of lines ever used getAdder on them, or 1 out of every 1,246 lines. So my claim is that there is not a yawning need for a new, easier spelling of getAdder. If somebody needs getAdder, they just call it. And if somebody doesn't need getAdder, they don't call it. And I don't think people need it very often. And I think that getAdder is fine. The other thing is that someone proposed, actually it was Calvin Spielman, name I don't know, and other people improved on the proposal. This idea of an AdderView object. The idea is that you have a constructor called AdderView, you pass in your object, and it returns a view object. The view object is implementing the mapping protocol, and it's behaving just like what we were talking about before, except we don't have the dots. The view object, you use square brackets and you pass in an expression, and you get the attribute of O. And so this really gets you everything that the proposed syntax with the dot gets, except that, thank you, except that you don't need to change the language at all. And people were like, wow, that's really neat. We don't need to change the language. I kind of like this syntax. I might use that in my own code. And so people sort of walked away from it and said, what happened was Ben wrote up a proposal, like he wrote the original proposal, and then he wrote a summary of all the changes that had happened. And at the end, he wrote this nice summary. It was like, this is why it was rejected by the community. It was the nicest rejection anybody ever had. Now, what's interesting about this particular proposal is that it isn't necessarily dead. Just last week, in a conversation on Python Ideas, Guido said, you know, it might be nice to bring this back. Specifically, so he spells it x dot parentheses foo, not square brackets. But he said, quote unquote, exploring the pros and cons of x dot parentheses foo and its alternatives and variations would be a fine idea. So possibly, the name of this talk should have been The Python That Isn't Yet. Almost any of these proposals could come back at some point in the future if they find a champion who wants to take up the charge and fight with Usenet about it. Well, as long as we're not all dead. But there are some I don't think are coming back. Thank you. I guess, do I have time for questions at this point? Sure, if anybody has any questions after that. I bet they don't. Yeah, go home, you mugs.